The discovery and rapid evolution of Comet 3I/Atlas has quickly become one of the most fascinating astronomical stories of the decade, captivating scientists, skywatchers, and the general public alike. As the U.S. government shutdown came to an end, NASA resumed its observations and analysis, preparing to release some of the highest resolution images yet of this extraordinary object. These new images, captured by the powerful HiRISE camera aboard NASA's Mars Reconnaissance Orbiter, are expected to surpass even the stunning snapshots taken by the Hubble Space Telescope on July 21, 2025. With HiRISE normally used to photograph fine details on the Martian surface, its ability to precisely resolve features from millions of miles away highlights just how compelling 3I/Atlas has become. Scientists are eager to examine every pixel for clues about the comet's surface structure, material composition, tail formation, and the history of its long voyage through interstellar space. Even before NASA's upcoming release, excitement surged after astrophotographer Satoru Murata captured a breathtaking image of 3I/Atlas just before dawn this past weekend. His photo reveals extraordinary tail structures, fine filaments overlapping streams of dust, and hints of ionized gas that shimmer as they interact with the solar wind. On the right side of his image sits Galaxy NGC 4691, a faint but beautiful reminder of the vast cosmic backdrop against which this comet travels. This single shot, taken from Earth with exceptional skill and atmospheric conditions, underscores the remarkable visibility and brightness of 3I/Atlas. In astronomical terms, it is rare for an interstellar visitor to become bright enough for amateur and professional astrophotographers to study so clearly. But what exactly is 3I/Atlas, and why are scientists so eager to investigate it? The comet, discovered in early July, is the third interstellar object ever detected in our solar system, following the cigar-shaped 1I/Oumuamua in 2017 and the hyperactive comet 2I/Borisov in 2019. Its name, 3I, marks it as the third confirmed interstellar visitor, while Atlas refers to the telescope system that first spotted it. What makes it truly extraordinary is not just its origin beyond our solar system, but its unusually large size and rapid brightening. Telescope measurements suggest its nucleus is roughly 7 miles, 11 kilometers, in diameter, significantly larger than most comets that swing through our solar system. For comparison, 2I/Borisov had a nucleus only about 0.5 miles, 1 kilometer across. The fact that 3I/Atlas is more than 10 times larger than Borisov makes it the biggest interstellar object humanity has ever observed. Its age adds another layer of intrigue. Astronomers estimate that the comet could be more than 7 billion years old, older than our Sun, which formed about 4.6 billion years ago. This extraordinary age means 3I/Atlas may contain pristine material from the earliest era of planetary formation in another star system. It may predate the Sun by billions of years, making it a frozen relic from a time when the Milky Way was still relatively young. Determining its exact origin, however, is proving challenging. Scientists are not sure whether it came from the Milky Way's thin disk, a region where most stars, gas, and dust reside, or the thick disk, which contains much older stars. Each possibility paints a different picture of its birthplace and journey. If it came from the thick disk, the comet may have been wandering through interstellar space for almost the entire history of our galaxy. Tracing its origins is also complicated by the fact that its material has been altered by billions of years of exposure to cosmic rays. These high-energy particles continuously bombard objects traveling through space, gradually changing their chemical makeup and sometimes darkening or reddening their surfaces. For 3I/Atlas, this means its outer layers have likely been reshaped into complex organic compounds and irradiated minerals that make it harder to determine what it originally looked like in its home system. However, studying these altered layers still provides valuable clues about the harsh conditions of interstellar space and the resilience of icy objects traveling great distances. The comet's speed is equally astonishing. Moving at more than 130,000 miles per hour, 210,000 kilometers per hour, it sweeps through the solar system at a velocity that far exceeds that of most native comets. This tremendous speed is not due to the sun's gravity, but to the comet's high incoming energy from interstellar space. Objects bound to our solar system travel on elliptical orbits, but interstellar visitors travel on hyperbolic trajectories, meaning they fly in from deep space and eventually leave forever. 3I/Atlas passed its closest point to the Sun, its perihelion, about 2 weeks ago, and is now heading toward its closest approach to Earth on December 19th. Even at its nearest, it poses no danger to our planet, but it will give astronomers a spectacular opportunity to study it before it disappears into the darkness of space, never to return. Its rapid brightening, unusual structure, and strange chemistry have led to a wave of public speculation and conspiracy theories, including claims that the comet might be an alien probe or artificial object. The presence of radio signals, which are completely normal for comets emitting charged particles, has only fueled these rumors. When comets interact with solar radiation and solar wind, they naturally produce radio emissions in specific frequencies due to ionized gases like hydroxyl OH. These emissions have been detected many times before in ordinary comets. Yet, because 3I/Atlas is interstellar and already wrapped in mystery, some people have taken these scientifically expected signals as something more exotic. Astronomers, however, have been quick to point out that nothing indicates artificial origins. Its behavior is entirely consistent with that of a natural comet, albeit one with larger size and more dramatic features. Still, natural or not, 3I/Atlas is offering researchers a once-in-a-lifetime opportunity. By studying its dust, gas, and tail dynamics, astronomers can gather information about the conditions that existed around other stars billions of years ago. The chemical composition of its coma, the cloud of gas and dust that surrounds its nucleus, can reveal the building blocks present in the comet's home system. Some early observations suggest that 3I/Atlas contains unusual proportions of carbon-rich compounds, potentially indicating that its parent star or disk environment had a different chemical balance from our own. If confirmed, this would be a groundbreaking insight, showing that planetary formation elsewhere in the galaxy can produce very different types of icy bodies. Scientists are also interested in how the comet responds to solar heating. Because it formed in a completely different star system, its ices may have different sublimation points, meaning they evaporate at different temperatures. Observing how its tail behaves as it approaches and retreats from the Sun allows astronomers to test theories about exotic interstellar ices, volatile compounds, and the physical structure of ancient cometary nuclei. The intricate tail structures captured by Murata's photo hint at multiple layers of dust release, possibly even fractures or vents in the nucleus that produce distinct filaments. These patterns give researchers valuable clues about the internal structure of the comet, such as whether it is a monolithic object or a collection of loosely bound rubble. The scientific significance of 3I/Atlas cannot be overstated. Interstellar objects are extremely rare, and studying one up close offers insights into regions of the galaxy far beyond the reach of spacecraft. By analyzing its trajectory, scientists can also learn about the gravitational influences it encountered along its journey. Small perturbations in its path might reveal past interactions with stars, planets, or dense molecular clouds. Each of these interactions leaves a subtle signature that expert dynamicists can decode to reconstruct possible routes the comet may have taken over billions of years. Moreover, 3I/Atlas helps astronomers refine their understanding of how common interstellar objects are. For decades, scientists believed such visitors were exceptionally rare. But with 3 discovered in a span of less than 10 years, it seems the galaxy may be filled with icy travelers wandering between star systems. This realization has major implications for planetary formation theories, as it suggests that young planetary systems may eject far more debris into interstellar space than previously imagined. These rogue objects could transport organic materials and complex molecules from one star system to another, contributing to the chemical enrichment of the galaxy on cosmic timescales.